How do the components of a CPU communicate? Inside a modern processor, components like the program counter, accumulators, and data registers constantly exchange information to execute programs. But here's the challenge. How do we manage this high-speed traffic without creating a tangled mess of dedicated wires for every connection? Imagine if every register needed a direct, dedicated path to every other register. The number of connections would be unmanageable and impossible to scale. With just 4 registers, you'd need 6 connections. With 8 registers, 28. With 16, 120. It explodes quickly. There's a better way, the shared highway. Instead of a separate path for every conversation, we create a single, shared communication channel, a common bus. Anyone can place information onto the bus, and anyone can listen. The key is controlling who gets to speak at any given moment. Enter the multiplexer, a smart switch for data. The multiplexer is the core component that enables our bus system. It selects one of several input signals and forwards that selected input to a single output line. The choice is determined by the value of the select lines. Think of it as a controllable gate. Let's build our bus. We start by taking the first bit, bit 0, from each of our 4 registers, A, B, C, and D, and connecting them to the inputs of a single 4 by 1 multiplexer. The select lines S1 and S0 determine which register's bit 0 appears on the output. Now we repeat this pattern for every bit position. We need a dedicated multiplexer for bit 1, bit 2, and bit 3. Each multiplexer handles the traffic for its bit position, and their outputs collectively form our 4-bit common bus. 4 registers, 4 bits each, 4 multiplexers, elegant. This is our elegant solution, a scalable and organized system where 4 registers can share a single communication pathway, all controlled by a simple set of select lines. The common bus acts as the highway, and the multiplexers act as the on-ramps. Now let's see how it works. Our task is to copy data from register A and place it into register B. This is a 2-step process involving the select lines, the bus, and a control signal. Step 1. Place the source data on the bus. To select register A, we set the select lines S1, S0 to 00. This commands every multiplexer to choose its 0th input, which is connected to register A. The contents of register A are now broadcast onto the common bus, available for any destination. Step 2. Enable the destination register to receive. The data is on the bus, but who is listening? A load signal from the control unit tells a specific register to accept the data from the bus. By activating the load signal for register B, it copies the value currently on the bus. Transfer complete. The control unit uses this simple binary code to determine which register's data is placed on the bus at any time. 00 selects A, 01 selects B, 10 selects C, 11 selects D. 2 select lines give us 4 choices, exactly what we need. Architect's rule number 1. Register width determines the number of multiplexers. Our 4-bit system required 4 multiplexers. A system with 16-bit registers would require 16 multiplexers, 1 for each bit position. The pattern scales perfectly. Architect's rule number 2. The number of registers determines the multiplexer size. The size of each multiplexer equals the number of registers. Our 4-register system used 4 by 1 multiplexers. A system with 8 registers would require 8 by 1 multiplexers. By starting with the problem of connectivity, we arrived at an elegant solution. The common bus acts as a shared highway, while multiplexers serve as the traffic control, governed by 2 simple design principles. This is how computer architecture creates order from complexity. If this clicked for you, hit subscribe. Thanks for watching.